Today I'm going to be solving this problem, and it may not be very interesting. It looks like it's just one more trigonometric equation that I'm doing, but I think maybe we can say some interesting things here. Starting from the fact that unlike most of our trigonometric equations problems, he's not asking me to find the value of x. He is asking for something that looks a bit arbitrary. Sine of x plus cosine of x. Of course, if I knew x, then finding sine of x plus cosine of x would be easy. But generally, that's not what happens in this type of problem that asks for an arbitrary looking expression. Usually, you don't get to find x to then find the thing that you want. You usually have to work around the x a little bit. So as I go through the problem, I'm going to make a list here of the tools that I'm using to solve that problem, and I think it's going to be a list of 4 tools, because that's the interesting thing that I wanted to point out about this problem. Every tool that you learn it in isolation. Like, this is what you should do when you have this kind of situation. And then maybe you have a worksheet in which you get to do that 10 times. But repetition is not the difficulty, is it? Solving problems is difficult because you have to choose which tools you are going to use out of the many tools that you have previously learned in isolation. So in this one, we're going to need 4. So I think it's going to be kind of a nice problem to solve, even though it's not really like we're going to be needing to choose what tools we're going to use, okay? All of them are going to be pretty obvious when the situation presents itself, and that is also something that you should keep in mind when solving problems, I guess. If something looks obvious, try it, just so you understand what kind of thing I'm talking about. The first tool that is standing out to me in this problem is those hidden quadratic equations. Do you see it? When we multiply both sides of the equation by the tangent of x, this is going to turn into a quadratic equation in the variable tangent of x. And since I have an x in the denominator, this is always one of the things that I try to get rid of first. It's not really like I'm having an idea. It's not really like I'm choosing what I think is going to be the best strategy from this point. I'm just doing what feels obvious. But before I continue to go down this path, let me make a couple of non-obvious observations that are also not essential to solving the problem, okay? I'm going to say these things because they are pretty, but if you didn't notice any of that when solving the problem and really just went with the obvious sequence of steps, you would maybe have a little bit more work, but it wouldn't stop you solving the problem. So the first thing that I want to say here is that tangent of x and 1 over tangent of x are 2 numbers that have the same sign. If one of them was negative, the other was also going to be negative. And in this case, we know that they are both positive because they are adding up to a positive number. In the case of tangent, that means that the angle x is either in the first or the third quadrant. And what that means for sine and cosine, which are the ones we're going to want later, is that they have the same sign. First quadrant, they are both positive. Third quadrant, they are both negative. Also, because of the format of this equation, notice that if tangent of x has a certain value, then 1 over that value is also going to be a solution to the same quadratic equation. For example, if the value of the tangent that is one of the solutions is called p, then p plus 1 over p is 8 over 3. But that means that 1 over p for a tangent plus 1 over p, that's also going to give another solution because this is just p. And that is also equal to 8/3 because it's the same addition. Now, because these p and 1 over p are going to be representing a value of tangent of x, then one of them is sine over cosine and the other one is cosine over sine. It might be the other way around if you're considering the other solution of the quadratic, but it's not going to change the final answer to your problem because either way you're going to take the sine plus the cosine. So it's either the numerator plus the denominator or the denominator plus the numerator, which is the same answer. Which means that in the end, you're only going to have to consider one of the solutions of the quadratic. Which is why I said that these observations would save you a little bit of time, because if you didn't notice this, then you would want to consider both solutions. But that's all. That wouldn't stop you from solving the problem. And speaking of noticing things, there is another solution to this problem that's different from the one that I want to show you. That comes exactly from noticing that the tangent is sine over cosine and the other one is upside down, so that it becomes cosine over sine. Now, if you want to put those two fractions together, you probably have to put them into the same denominator. So when you do that, you get a numerator that is sine squared plus cosine squared, which is 1. Now you can just turn this equation upside down, and sine times cosine is not the thing that you want, but you can leave it there for a minute while you go back to thinking about the sine plus cosine, which is the one that you want. Now, the way that this one is going to be helpful in finding this one is if you actually try to find the square of this instead, and then at the end of the solution, you just have to remember to take a square root. But this we can use the special product. And now again, we are finding a sine squared plus a cosine squared, which is 1. And this middle term has the sine times cosine that we already know to be 3 over 8. So we just have to add the fractions here. 8 plus 6 is 14. We simplify this fraction. And this number 7 over 4 that we are finding is sine plus cosine squared. So the sine plus cosine that we were looking for is the square root of that, plus or minus root 7 over 2. Now, this solution is very elegant, and it is probably the solution that they wanted us to give, because this type of problem that doesn't ask you for a straightforward thing like find me x, but instead asks you to find an unusual thing like find me sine plus cosine, usually you don't have to find x, you don't have to find the individual things that you're wanting to add. You're usually just going to find a path that leads directly to the unusual thing that was asked. So this is a good solution, but it is also the type of frustrating solution that people a lot of times look at and don't think that they would have thought of that by themselves in an exam. And this is not what this video is about. I'm not here to show you a pretty and elegant solution. I am here to tell you what to do if you don't think of the elegant solutions. So I am much more interested in showing you a bunch of tools through a much longer and clunkier solution that I'm going to do. But those are tools that you can reuse over and over again in other problems that you will run into in the future. Okay, so it's not about solving the problem is already solved. But I do want you to pay attention to the tools and keep them in your toolbox to use again in the future. So anyway, like I said, the first of the obvious tools that we are going to use to solve this problem is the hidden quadratic equation, which I've already started showing you here when I multiplied both sides of the equation by tangent of x. Now I'm just going to multiply both sides by 3 to lose this other fraction and organize it a little bit. And finally, I'm just going to put the quadratic formula to find the values of tangent of x. Okay, that's an ugly looking number. Let's try to simplify it a little bit, because 64 minus 36 is 28, which can be factored into 4 times 7 to turn this into a third. Then I can cancel out a 2 from the numerator and denominator. And I wouldn't say that this number looks pretty, but it's as simplified as it's going to get. Now, I did say that the observations we made in the beginning were optional, but since we did do the observations, let's check if the answers that we are finding are doing what we expect from them. First of all, we said that they were both going to have the same sign, and this is happening because they are both positive. Even the one with the minus, the square root of 7 is much smaller than 4, so when you subtract, this is still positive. But much more surprisingly, we said that one of the solutions was going to have a value that was 1 over the other one. And this is not clear at all when you look at 4 plus or minus root 7 over 3. So this is something that we should check. Put a little question mark there because I don't know if this is true. I am trying to check. So first of all, dividing by a fraction is ugly. Let's flip this around with the 3 on top. And now we're going to use rationalization, which is an obvious tool to use at this point. The only reason why I'm not putting it in the list yet is because this part is optional. We didn't need the observation, so we didn't need to do this. But we are here, we are checking this calculation, so let's rationalize that fraction to see if it becomes the same as this one. Of course, that's the thing that you should multiply the fraction by in order to rationalize this kind of thing. We already know this because we've studied it a while ago. There's that special product happening here in the denominator. I chose not to do this distributive because I want to still see the 4 plus root 7. I want to compare to this one. But 16 minus 7 is 9. And this 3 is going to cancel out with one of the 3's from the 9. So there you go. Yes, both things are the same. Okay, so anyway, that was the first part of solving this problem when we used our first tool, and we found that these are the two possible values for tangent of x. But because of the observations in the beginning of the video, I know that I am allowed to choose just one to work with from now on, so I'm going to choose the one with the plus. Now, the second tool that I'm going to put on the list is one that is probably a lot less obvious than hidden quadratic equations, which is something that we see every day. So it is possible that you're going to see this next one for the first time now. But if that's the case, try to put it into your toolbox because it comes up over and over again and it's very useful. It's a simple trick for when you know one trigonometric ratio and you want another one. In this case, we have a tangent and we want a sine, and we also want a cosine, but it works for any of the ratios. If you have one, you can find any of the others. And the trick goes like this. You start by drawing a little right triangle with your angle x somewhere in there. And it doesn't really matter if you're sure that the angle x is an acute angle or not. Just pretend that it is. Because if it isn't, if it happens to be in one of the other quadrants, then the only difference is going to be maybe the sign of the ratios that you're finding. So maybe you find cosine equals a number, but it might be negative, that number. And then you will think about whether the numbers have to be positive or negative, not according to what happens here in the triangle. You will think about that in terms of which quadrants you know your angle x needs to be. For finding the numbers, the right triangle with the acute angle will be very convenient, and it is enough. So the next thing that you're going to do is to take the ratio that you currently have, which in our case is the tangent, which is the opposite leg divided by the adjacent leg. If we had a different one of the ratios, then we would be talking about a different pair of sides of this triangle, but there would always be two. And sometimes the number that you have here is not going to be a fraction like this. It might be in a different case where the tangent of x is equal to 3 or something. But often it is going to be a fraction. So the most convenient way to deal with this is to take the numerator of the fraction as the opposite leg and the denominator as the adjacent leg. Now the tangent of that angle is certainly this over this, which is the number that we have. And now you can use Pythagoras to find the length of the missing side of the triangle. In this specific example, we're going to have to be a little bit careful because this thing squared also requires one of the special products, but this is just a matter of paying attention and not making mistakes. Now we can collect all of those numbers here. 9 plus 16 plus 7 is 32, and that is the hypotenuse of our hypothetical triangle. This triangle isn't really part of the problem that we're trying to solve. We're just using it to figure out the other ratios of the angle that we're working with. And now that we have all three sides of the right triangle, we can get any trigonometric ratio that we want. In our case, we want the sine and the cosine. All I did was take for the sine the opposite leg divided by the hypotenuse, and for the cosine the adjacent leg divided by the hypotenuse. Now the problem is finished technically because he asked us to find sine of x plus cosine of x. So I'm just going to write this. So both fractions were in the same denominator, so at least there's that. And in the numerator we have a 7 now because one of the fractions had a 3 in the numerator and the other one had 4 plus root 7. So 3 plus 4 is 7. And technically the problem is finished. You could stop here if you wanted. But I do agree that it feels very unsatisfying to have such an ugly number as an answer. So if you want from here to simplify your answer a little bit, there's more tools that we can use for that. And the reason why this number looks very ugly right now is the double radical. You have a radical inside of another radical, And not that this matters so much, but this happened because this one came from Pythagoras and this one came from the quadratic formula. Doesn't really matter how we got to this point, but the thing is that I want to show you a tool for simplifying double radicals that, again, maybe you haven't seen it before because it's not as common as some of the other tools that I'm using. And also, I have to warn you that it's a tool that doesn't work in every single case, okay? Double radicals are not always able to be simplified, but this one is. So let me show you the tool. And by the way, it's not like I'm looking at this one and it's clear to me that this one will be able to simplify, right? I'm only saying this because I've done this calculation before recording the video, so I already know that it's going to work. But here's the thing. When you take a number of the form a plus b root c, and you square it, this has a tendency to keep having the same radical because of the special product that you're going to use. This is already integer, so 3 squared is going to stay as an integer. When you take this part and square it, it is going to be integer because the radical is going to be multiplied by itself. But then there's that middle term, which in this example will be 2 times 3 times 5 root 7. So whatever radical you have here, when you square, it's going to still be there. So I think that if I'm able to simplify this, it's going to be equal to something that has an integer plus another integer times root 7. Because when I square both sides of this equation, this is the type of thing that tends to happen. And from here, whether this is going to be one of the examples that works or not is going to depend on whether we are able to find values of a and b to make this equality true. Both sides of the equation have something multiplied by the square root of 7, so 8 had better be equal to 2ab. And on the other hand, the rest of the numbers I'm hoping will be integers, so 32 is equal to a squared plus 7b squared. This is an ugly looking sort of thing. It is a system of two equations and two unknowns, but it is not a linear system of two equations and two unknowns. If it was linear, then you just turn on another tool and solve it, but it's not. So when you have a system like this, in theory, there should be a solution. There should be a pair of numbers, a and b, that make both of these equations true at the same time, but there is no predetermined sequence of steps that is always going to take it to the answer. So it's a little bit of trial and error. You can start by simplifying here. The green equation can be divided by 2 on both sides. And now there aren't that many pairs of numbers that multiplied by each other is equal to 4. So if you just try the pairs that exist, you will see that 2 and 2 works. 2 times 2 is 4, and 4 plus 28 is 32. So we can put the 2 and the 2 back up here. And there you go, that's the simplified version of the denominator of our fraction. So I started solving this problem by telling you that I was going to use 4 tools. The first one happened to be a very well-known one, the hidden quadratic equations. And then I followed that up with 2 tools that are a little bit more obscure and maybe you hadn't seen them before. And now I'm going to wrap it up with a 4th one that is very obvious. And by the way, we have already mentioned it in this video because, of course, I want to rationalize this fraction. So that's the only thing that remains to be done. But I don't want you to come out of this video thinking that I have just solved a very interesting problem by being very smart and that you would have never thought of that. Because that is the most frustrating feeling in math, is when you see things and you understand what's being done, but you wouldn't have done it by yourself. Let's take away something different from this video, okay? I did not think of these tricks when I was solving this problem. I had seen them before. Seeing a double radical and deciding to do what I did, to me, is as natural as seeing a quadratic equation that is hiding and doing that, which is the part that I'm pretty sure you did because you've seen it before. So when you see somebody using a tool that you are not familiar with, it can feel like that person is coming up with the tool at that moment. But I want to assure you that that is rarely the case. So what you should take away from this is that maybe you have learned 2 new tools. And maybe the next time in your life that you face a double radical, you will know what to do because you've seen this before. Maybe the next time that you have a tangent and you want a sine, you will use the trick that I use of drawing a right triangle because now you've seen it before. Whenever you see something that looks new to you, try to make it old. Don't just discard it as, oh, this one I didn't have. That's how you're going to increase the number of things in your toolbox, okay? So let's go ahead and rationalize this fraction. You could do it like this, but I think that's just too many twos. So let me, before rationalizing, just factor out a 2 from the denominator here. That should make the calculations a little bit easier. So in the denominator, I'm going to have the 2 and then the result of this special product here, which is 1 minus 7. And then you can check if I didn't make any mistakes in the distributive for the numerator. Anyway, 7 minus 7 cancels out. And this minus 6 here is also going to cancel out with this minus 6. And the final answer is root 7 over 2, which is a very satisfying answer for a problem that went through such ugly numbers along the way. Now, if you remember that in the beginning of the video, I mentioned that the tangent was going to be positive, but the angle x could be either in the first or the third quadrant. This is the answer in the first quadrant because both sine and cosine were positive. So when you add them up, it's a positive number. If they were both negative instead, then you would have found the negative version of the number. So I'm fixing that by putting a plus or minus. And the place where I lost the plus or minus was in the right triangle, okay? It was not because I only chose one of the solutions to the quadratic equation. The other one was positive as well. The tangents were always positive in this problem. But in the right triangle, and I mentioned that when we were talking about it, we were assuming that the sine and cosine were positive because we were assuming first quadrant there. But then we have to remember at the end that the angle x did not necessarily have to be in the first quadrant. It could also be in the third. But in this case, the only thing was to stick a plus or minus there because in first and third quadrant, they have something in common, which is that sine and cosine have the same sign. If it was something like the second quadrant, then you would have had probably to do something minus something else there and come up with a different number in the end.